Welcome, it's Tuesday, August 18th, and today we're going to do the domains of composite functions. The past few lessons have been laying the prerequisite work that you needed to know in order to do the domain of composites. Okay, here is our summary of our rules when we have to worry about domain, and it all has to do with any situation where you have an expression that if you plugged a number in and tried to calculate a value, you would get an error. Okay. All right, finding the domain. So we've done these types of problems. I'd pause the video, work through them, and then see how you do, and you can kind of gauge what your understanding is on how to find the domain of functions. All right, hopefully you did well. Here are the solutions. The first three were problems that we did a while back. I had to set, for each one of these, I had a variable in the denominator, so I had to set that denominator not equal to 0 and then solve it. So in this one would be all real numbers except 0, all real numbers except -6. When we have an expression under a radical, it's allowed to be greater than or equal to 0. So this would be all numbers bigger than or equal to 0. Same deal with number 4. That expression has to be greater than or equal to 0 after you plug the x in. So we solve it, and we get x is greater than or equal to -4. So there's our interval. Now the next two are like what we did yesterday, where we had non-linear equations. So 1 minus x squared is a parabola. So you had to, in order to solve this, you had to solve a quadratic inequality, which you can do by either graphing or by using a sign chart. If we graph that equation right there, 1 minus x squared, it would have looked something like this. And where it crosses is at -1 and 1. So we want to know what x values is this graph positive. Well, I can see up here that to the left of -1, the graph is negative because it's below the x-axis. Then after I pass -1, it becomes positive. And then when I pass +1, it becomes negative again. So I can see that the positive, if I pick x values between and including -1 and 1, then I'm going to get a positive result, which is okay to have under a radical. Okay, number 5 was solved the same way. Okay, in this case I factored out an x, and I got two expressions, an x and a x plus 3. Okay, the roots for that, what would make this thing equal to 0 would be a value of 0 for x or a value of -3. So those are my roots. Laid those out on a number line, and then I pick a test point from each one of these intervals to get my signs. So for example, I could pick a number like -4, plug it into these two, negative. Pick a number between -3 and 0, like -2. Plug it into those, I get a negative and a positive. When these get multiplied like they are right here, that gives me my sign. And then the last one, if I picked a number greater than 0, each one of these things would be positive. So I am looking for, where is the graph positive? Well, it's positive to the left of -3. And it's allowed to be equal to 0, so that's why I use the brackets. And then it's positive to the right of 0 up to infinity. Okay, when we do compositions and we want to find the domain, so the key understanding of compositions is, if I'm composing f and g, we refer to as g as our inner function. All right, so what happens is we put something into G, then it comes out, it becomes the output of G, or the range, and then that has to be within the domain of F, and then when that comes out, we get the range of the composition. So whatever goes in initially has to be part of the domain of G. Then whatever comes out of G has to also be part of the domain of F. Otherwise, it won't be able to go into F. So the output from G becomes the input of f of x, or the range of G becomes the domain of f of x. So when we are considering the domain of a composite function, we have to take in consideration the inner function and then the final composite function. So finding the domain of a composite function consists of two steps. Our first step is going to be find the domain of the inner function. If it has any restrictions on it, then we're going to keep those. All right. Then we construct the composite function and we calculate the domain of that. Okay. Then what we do is we look at the domain of the inner function and the domain of the composite function, and we combine those. Okay. Now, if there's an overlap between the two domains, okay, then we use the more restrictive domain, which is the overlapping part, and we'll see an example of that here in just a few minutes. Okay, so here is your two functions, f of x and g of x. And the first thing we're going to do is do the composition f of g. So g is the inner function. It's going to go into f. So basically what I'm going to do is wherever there's an x in the f function, I'm going to replace it with the expression 5x minus 39. Okay, and the way we would write that out, we'd say f, the input to function f is actually function g. Right? So that's f. I take out g of x, and I put in what it's equal to, 5x minus 39. Now, I'm going to take that 5x times 39, or minus 39, and put it in each instant of x. So I'd have 4, 5 minus 39, and then I'd have 5x minus 39 plus 6. Now I'm going to simplify that. So our composite is equal to this expression, and I just simplified it. Okay, now what we're going to do is do the domain. So we first do the domain of the inner function. Well, there's no restrictions on this. This is simply a diagonal line, so there's no restrictions on g. So g of x has no restrictions. So now the only thing restricting this function would be the final composite, which is the 20x over minus 156 right here. All right, so g of x has no restrictions, so there's nothing to combine. Okay, its domain would be all real numbers. So now when I look at my composite, it's just like what we were doing the last couple of days. All right, that's a fraction, it's a rational expression. Its denominator cannot equal 0. So to get the domain of this, I'm going to take the denominator and set it so that it does not equal 0, and then solve the resulting inequality. Okay, so my domain are all the numbers except that one. Okay, so 33 over 5, that's going to be somewhere around 6. So I'm just going to say 33 over 5. Okay, that cannot be 0, so I've got an open circle. So now my domain is going to be anything to the right of that and anything to the left. So I would describe that as negative infinity up to but not including 33/5, or 33/5 and bigger. And there's the domain for my composite function. So this problem really didn't have anything new in it because the inner function didn't have any restrictions. Okay, now up here I attached, and I did it on your Google Classroom, a GeoGebra applet that shows you how this works. So I typed in the two functions here, g of x and f of x, and I graphed g of x. That's the yellow line there. So we can see that that has no restrictions in it. All right. The f of x, that's this green function, this rational function. Whoops. Now, if I wanted to know what does the composite of this look like? All right, so I'm going to turn these two off, and then over here, you guys can't see it because of my screen. Let me do this. I can click on these and get my composite. So the top one in that red is the composite. So I clicked on that. Domain of our composite, the composite is this red graph. The domain of it are all real numbers except 33 over 6. Well, 33 over 6 is around 5.5. So if I had a vertical line right here at 5.5, that turns out to be a vertical asymptote of this graph, and the graph will never touch that. Okay? So that's what the domain looks like of the composite. Okay, so again, we're doing a composite right here. So I'm going to rewrite f of g so that's f of x plus 3. Now to evaluate that, every place where I see an x in f, I plug in g. So this is going to be square root x plus 3. And that's my composite. All right, now to do the domain, I start with the inner function. Well, that's another line. So it's just like the last one. There is no restrictions on g of x. So this is an easier problem to do. On the next couple, these are going to have restrictions, but right now, no restrictions. So the only thing that I need to be worried about is doing the domain of the composite. So I'm just going to calculate, well, what's the domain of this? Well, x plus 3 has to be greater than or equal to 0 because it's under a radical. So x has to be greater than or equal to -3. So there's my domain. It's allowed to equal -3, and then it's going to be all the values that are bigger than -3, which would be to the right. And so I could express this domain as bracket -3, infinity. So really nothing new on these last two problems because the inner function had no restrictions on it. So these are sort of the simpler versions. All right, first let's do our composite function. All right, wherever I see an x in this function, I'm going to replace it with 2 divided by x. So I'm going to have 5 in my numerator and 2 divided by x plus 9 in my denominator. Okay, we can probably simplify this a little bit. So one strategy is to get rid of that fraction in the denominator. So if I multiplied the entire denominator by x, I could get rid of that fraction. Well, if I multiply the bottom of the fraction by x, I have to do the same thing to the top. And I'm just doing this so we've got a little bit more friendly expression or equation to work with. So my numerator would be 5x, and when I distribute this through, I would have 2 plus 9x, and that's my composition. All right, now what I'm going to do is first find the domain of my inner function. So in this case, my inner function is g of x. So the domain of g of x is not allowed to equal 0. So in interval notation, that would be -infinity to 0, not including 0, or from 0 to positive infinity. All right, so I'm going to keep that because I've got some restrictions. Now I'm going to do the restrictions on the composite. Okay, so my domain of the composite, all right, this denominator is not allowed to equal 0. Okay, so I subtract 2 from both sides, divide by 9, and x cannot equal -2/9. So I can say my domain of the composite Now what we want to do is combine these, and if there's any overlap, then we just are interested in the overlap of the two. Okay, now we want to find out if there's an overlap of these two domains. So I'm going to graph both of them, I'm going to color them in, and then any areas that are colored both, that's going to be the domain of our function. All right, so the first one was the domain of 2 over x. So I've got that drawn up here. So this is g of x. So its domain was everything except 0. So here's 0. So any numbers to the right of 0 would work. That's from 0 to infinity. Color that in yellow, and then from negative infinity up to but not including 0. Now down below we have a similar domain, but it's negative 9 over 2. It can't equal negative 9 over 2. So I would color to the right of this. Okay, that's that's this section right here, and to the left of that. Now, anything that is both yellow and green is going to be the domain of our composite. All right, so if we go this green section right here and this yellow section up to negative 9 over 2, it's both green and yellow, but not at 9 over 2. Okay, it's yellow, but it's not green, and it has to be both. So the first section, or the first interval of my composite, is going to be from negative infinity up to, but not including, negative 9 over 2. Negative 9 over 2 does not work in the composite. It works in the inner function, but it doesn't work in the composite. All right, now as soon as I leave negative 9 over 2, oh, they're both colored again. Green and yellow, green and yellow, green and yellow, yellow, no yellow, but green. So this cannot be in the domain. So anything in between these two numbers is both yellow and green. So I can put that in my domain. So from negative 9 over 2 to 0. And then as soon as I leave 0, they're going to be green and yellow again. So that would be represented by the interval from 0 up to infinity. And there now is the domain of my composite. First, find the composite of these two functions. So this tells me wherever I see an x in f, I'm going to replace it with the expression x squared plus 3x. So that's going to be square root x squared plus 3x. And there's my composite. All right, now we do our domain. So we do the domain of the inner function and then the domain of the composite. Okay, so the domain of my inner function, well, if I graph that, that would be a parabola. So it has no restrictions, which is good news because it's less work. We don't have to worry about any kind of overlapping now. All we have to worry about is what's the domain of the composite. All right, so to get the domain of our composite, well, this is under a square root, so it's got to be greater than or equal to 0. So this was the exact same expression that we did in the warm-up at the very beginning of class. All right, I'll go through it again. So to solve this, I'm going to factor out an x, and this would be x plus 3 is greater than or equal to 0. Okay, now the zeros of this, or its roots, would be if x was 0 or if x equaled -3. So I'm going to do this using a sign chart instead of graphing. 1, 0 is x equals 0, and then the other 0 is x equals -3. Right? All right, so we got two factors. We have an x and we have an x plus 3. So now I choose test numbers from each of these three intervals here. So I pick a test number that is less than -3, like -4. Well, if I put -4 in for x, it's negative. If I put -4 into this, that would be negative. And a negative times a negative is positive. Now, these equations, because it's got the equals on it, I know that these two are going to have solid dots on them. Those numbers are allowed to be included. Now I go to the middle section and I pick a number like -1. That's between these two. So if x is -1, it's negative. If x plus 3, if I plug in -1, I get a positive. Okay? So that's telling me that my graph is less than 0 here. My composite, okay, is less than 0 because of the negative. Over here, my composite is greater than 0, or my this expression here, I'm sorry. I shouldn't have said greater than 0. Let me clean this up. Okay, this is telling me that x squared plus 3x is less than 0, and that plus sign is telling me that x squared plus 3x is greater than 0. And it's equal to 0 at the two dots. And then over here, pick a number greater than 0. X would be positive. X plus 3 would be positive. So this positive is informing me that the expression x squared plus 3x is greater than 0 if I pick numbers to the right of 0. So the part that I'm interested in is where my graph is greater than or equal to 0. So that would be including -3 and to the left, and including 0 and to the right. So I would write that as -infinity up to and including -3, so bracket, or 0 up to infinity. And that's the domain of my composite. All right, guys, that takes care of Tuesday, the 18th, and finding composites of, or domains of composites. So your assignment is Math Excel, finding domain of composites, and the ones that you just have to be careful of are like the example that I did here where you've got the overlap. Okay, so you're going to run into something like that on number 1. Okay, so let's do that one again because these can get a little confusing. All right, so I'm going to do my composite. All right, and then I'm going to figure out my domain. All right, so here's number 1. I first did the composite. So wherever there was an x, I substituted it with 1 over x. Then to make this a little bit more friendly, I multiplied the top and the bottom by x, and I end up with 8x over 1 plus 8x as my composite. Then I go on to the second part, is find the domain. So you're doing the domain of the inside function and the domain of the composite. Notice that you're not doing the domain of the outside function. All right, so the domain of g of x is simply all real numbers except 0. And I graph that right up here. This is the green. Anything to the left is 0, anything to the right works in g of x. Then I did the domain of the composite. So our composite function, its denominator was 1 plus 8x, so that's not allowed to equal 0. So I solve that, I get negative 1/8. So x can be anything, just can't be negative 1/8. So I graphed that and I represented it in yellow. Now, these two domains overlap. Any part that is both yellow and green is part of my solution. So all the way until I get to negative 1/8, it's yellow and green. All right. But when I at negative 1/8, it's green, but it's not yellow. So that point is not in my domain. So the first part of my domain is going to be from negative infinity up to negative 1/8. Then the next part of this that's colored both is as soon as I leave negative 1/8 until I get to 0. Then it's not green but yellow. So any value in that little interval, not including negative 1/8 and 0. And then once I leave 0, they're both yellow and green again. So that would be from 0 up to infinity. So my solution, that's my domain. So hopefully that helped you out a little. Those are the only ones that are really kind of tricky. All right, take care, and we'll see you next time. Bye-bye.